Hello and namaste. My name is Brandon, and welcome to the next video in my series on basic statistics. In this video, we will learn about the log transformation, which is a common way to reshape our data so that it better meets the assumptions, in this case, of linear regression. Now keep in mind, this video is the next in a series, and I will not be going back and reviewing everything in the prior videos. So you might want to go back and watch those before watching this one. And finally, as always, like, comment, and subscribe. Let's get going. So remember that when we're dealing with transformations, in the case of linear regression specifically, what we're trying to do is get the data in a shape that is more normal. So the linear regression algorithm likes data that is normal and it performs better. So here on the left, we have right skewed data, which means we have a long right tail. On the right, we have left skewed data, which means we have a long left tail. Now the goal of our transformations is to make these look more normal, more like a symmetrical Bell distribution, and that way the linear regression algorithm works better. And you'll see that when we go into Excel at the very end and actually look at some numbers. So we're trying to unskew data to meet the assumptions, in this case, of regression. And of course, skewness can come in many varieties and many severities. So we have on the left here, we have right skew that's mild. Then we have right skew that's sort of moderate. Then we have right skew that's severe. And as you can see, as we move to the right, the tail becomes longer to the right. And then we can have the same thing going left. So we could have left skew mild, left skew moderate, and left skew severe, which we can see over here on the right. So log transformations. Log transformations are good for a moderate skew, and they are commonly used when there are a few large values. So oftentimes, like for income, because of the way income works in many countries, there are many individuals that have very, very high incomes and wealth, and therefore sometimes we take the log of income to make it a bit more normal for our analysis. Same thing with population. So here in the US, the population in terms of state is dominated by a few large states like New York, California, and Texas. So oftentimes we will take the log of population to make it more normal. Log transformations are very, very common. So keep in mind that when doing log transformations, the values cannot be less than 1, and that is just the nature of logarithms. Also keep in mind that log is sometimes written with the base number and sometimes without. If it is written without the base number, we assume that it's log base 10. So log base 10 of 1 is the same thing of just log of 1, and of course that equals 0. So here you can see why we have to have values that are at least 1, because the logarithm of 1 is 0. Also remember the nature of logarithms. So if we take the log of 1, that is 0. The log of 10 is 1. The log of 100 is 2. And the log of 1,000 is 3, and so on and so forth. That is why we often refer to logarithms as measures of magnitude. Now, log base 10 of x or log base e of x can be used. Now remember, or we could use another base for that matter. Remember that log base e is the same thing as the natural log. So when you see that ln of x, that is log base e. And it's just another way of doing a logarithm. So technically speaking, the log could be any number so long as it meets the requirements and we don't have any values that are undefined or throw us an error. Now, oftentimes a constant is used so that the smallest value is 1. So if we have our data and we do the minimum for the values in that column or in that variable, and we have values that are less than 1, oftentimes we will just add a constant to that and then take the logarithm. So for example, if the smallest value is -4, then the first step might be to add 5 to each value before applying the transformation. That way we don't have any undefined values and Excel or whatever software we're using won't give us an error. Now, if the variable is left skewed, so a long left tail, then the variable is also reflected to be right skewed. So a lot of these transformation functions work assuming that the function goes to the right, and therefore what we will often have to do is reflect the variable. So if the variable is left skewed, we will have to reflect it first before applying the transformation. I covered reflections at great length in the prior video, so go ahead and check that out, and I will put the link here in the cards and or in the comments. So the overall process might be to shift it to a minimum of 1, reflect it, and transform, or some combination of those. And of course, when transforming variables, we must always keep track of the changes we are making from the original data. That's because we have to know how to interpret our output, we have to know how to communicate those results to any stakeholders, and make sure we're not doing anything incorrectly. So, as transformations are done, always keep track of what you are doing, whether that is naming the variables a certain way, or taking notes, or whatever else you might need to do. If you're working with many variables, it can get very confusing. So here's the data we're going to look at in this video. This is from the Boston dataset, which I will talk about here in a second. But this is the histogram of the variable distance in the Boston dataset. So remember, the Boston dataset is a very common dataset that I've used in this video series. And of course, if you do data science, you see it all over the place. So as you can see, the vast majority of the houses in this housing dataset are close to the center from measurement. And then we have fewer and fewer as you go out from the center. Now, if we're going to use this data in, say, a regression problem, what we want to do is make this more normal. So it's very, very highly right skewed at this current stage. So what we'll do is apply the transformation and see what happens both visually and numerically. So a tale of transformations. Now, the square root, which we covered in a prior video, the logarithm, so log base 10, and the natural log, which is log base e, all those functions do similar things to the original data. Now what it is that the flatness of those functions indicate the magnitude by which larger values are smashed down, making the data set less right skewed and therefore more normal. So here in this graph, we have 4 lines. The purple line is just a straight line of x. So when we graph 1 on the x-axis, it's 1 on the y-axis. 2 on the x-axis is 2 on the y-axis, so on and so forth. It's kind of an identity. That's our starting point. The orange line is the square root function. So you can see that it goes up and then it bends to the right and flattens out. Now we covered the square root transformation in the prior video, so please check that out. Now the blue line at the bottom is the logarithm, or log base 10. You can see that it's very flat as it goes to the right. And then the green line is the natural log, which is sort of in between those two. Now you'll notice here that I actually graphed log of x plus 1 and natural log of x plus 1. And of course I did that so that the minimum value is 1, so that the graph actually makes sense and meets at the origin there. But what we're really interested in here is the overall shape of each function. So what happens is when we do the log transformation, or even the square root transformation for that matter, we bring in the transformation hammer. And what the transformation hammer does is it goes up to the higher values there and really smashes them down. And visually what happens is it brings those large values in closer to the center, closer to the smaller values, and has the result of making the distribution more normal. So it really flattens out the further right you go. So here we have some toy data that I use just to kind of show how each value is related to the other values. So in our start data in the purple here, we have a hypothetical set of 11 data points that are evenly spaced. So 0, 10, 20, 30, 40, 50, and so on. That's represented by the purple dots under start over here on the right. Then if we apply the square root transformation, the relative distance between each data point or each dot changes. So we can see that in the square root transformation, the lower values tend to spread out, the higher values tend to clump together. So what that does is it pulls in those higher values more towards the center, and the result is a more normal looking distribution. Now in the log transformation, we can see that that happens to a greater extent. So the higher values really get compressed together. And then the natural log is sort of an in-between. So the higher values are compressed together, but not as much as the log base 10 and more than the square root. So it's kind of in the middle. So overall, what we have happening here is an expansion in the lower values and a compression in the higher values for these 3 transformations. It's just a matter of degree, but the basic idea is the same. We're changing the relative space or distance between each individual value by applying the transformation. So let's talk about compression slope. Now, If you're not interested in kind of understanding why it works, just kind of close your ears for a minute or two, but I do want to explain to individuals who are interested what's actually happening here. So over here on the left, we have a graph of the logarithm, just log x. Now, just keep in mind that I did graph log x plus 1 to move it up just so it's easier to see. But the shape of the curve, the shape of the line is the same. I just did it for visual purposes and it's easier to see, like I said. If we have this function, log of x, so log 10 of x. If we take the first derivative of that, we have this. 1 divided by x times the natural log of 10. That is the first derivative of log 10 of x. So what does the first derivative give us? Well, it gives us the slope of the tangent line of log x. So what happens is that if we take a low value here, like at 1, the slope of that tangent line is 0.43. If we take a higher value, let's say 4, the slope is 0.11. But what's happening? It's flattening out. If we take 9 here, then we have a slope of 0.05. It really flattens out. And of course, it will just keep going. Now, what happens here is as the values get larger and larger, we're compressing them more and more. And we can actually tell that mathematically by the very simple first derivative of a transformation function. We did the same thing in the square root function before. Now, if you don't really care how it works, you don't need to really know this, but I do want to explain what's going on mathematically and how it actually works. And we can tell that in this case by looking at the slope of the first derivative, which is the tangent line. So just keep in mind, we are using the Boston dataset, which appears in nearly every data science tutorial or book you might see. It's a very commonly used dataset. In this video specifically, we are using the distance variable, which is the weighted distances to 5 Boston employment centers for the homes in this dataset. Now, here's what happens when we apply the transformation to the distance variable. So here is the original histogram, which we saw before. Now, if we go ahead and apply the log transformation, here's what we get. Almost a normal distribution. All we did was take the log of the distance. So of course we checked to make sure there were no distances that were less than 1, which in this case there were not, and then we went ahead and took the log. So now instead of this highly right skewed distribution on the left, we have an almost normal distribution over here on the right. And that's exactly the goal of doing transformations, at least in the case of linear regression. So let's hop into Excel quickly and I'll show you how this actually works numerically and how taking the transformation changes the relationship between variables. So let's do that and then we'll come back here and finish things out. So here we are in Excel. Remember, you can download this file and follow along and do your own work if you like. That link is in the description. Now, I'm not going to go through me typing everything in and bore you to death. So I'm just going to show you what I did and then show the output. First thing to keep in mind is that in the top column here, we have our variables, and then underscore T means I have transformed it. Now, in this case, we have DIS for distance, and then DIS underscore T for transform. If I click in the first cell here, then you can look, you probably can't see that on YouTube, I am sorry, but all I did was take the log base 10, the logarithm of the values in the original distance column. So in this case, it is just the logarithm of whatever's in column M, and that's what we have here. Now, as we go over, we can see that I have done other transformations for other work I've done and other videos. So in the previous video, we looked at PT ratio. We did the square root transformation for that one, and you can see that data appear on the right. So in this case, we did the log transformation. Now over on the right, MEDV is sort of our dependent variable, it's our target variable. So we have the original MEDV in column X, and then we have the square root of that variable in column W. So what we will do is do a correlation between all combinations of those variables. And we did that. So it's over here on the right. Keep in mind that here are the original histograms and then the log of the distance, which we saw in the PowerPoint part of this. So we're interested in these values here. So what I have here is a set of correlations between all combinations of the original distance variable and its log transformation, and then the original dependent variable or target variable, which is median home value, and its transformation. Now what we have here in this first line is the correlation between the two original versions of the variables, so the original distance and the original median value of the home. We can see here that the correlation is about 0.25. So that means, in general, as the median value of the home goes up, its distance from as measured from those business centers also tends to go up. So that's kind of what we're saying here. If we go ahead and do a correlation between the original distance variable and the transformed median home values, remember the median home values in this data set were skewed as well. So many homes were towards the lower end of the distribution, so it was right skewed also. So we went ahead and took the square root transformation of that variable. Now the correlation is 0.3. That's quite a big jump. And all we did there was take the square root, apply the square root transformation to the median home value, and we gained 0.05 in correlation. That's a pretty big jump. Now the next line here is the log of the distance and the original home value, do that correlation, and now we have a correlation of, again, 0.3, if we go ahead and round up approximately. So that's about the same as the one before it. So we have got an increase in the correlation by doing that. And finally, in the last line, we have both variables transformed. So log of distance, square root of the median home value. So two transformations to make those more normal. And now we have a correlation of 0.35. All we did there was do transformations. And then we can see that we gained a tremendous amount of linear relationship, or the strength of a linear relationship, just by doing the transforms. We went from 0.25 to 0.35. Now by increasing the correlation between these two variables, we've made both of them more normal. When in this case we perform linear regression, what we've done is sort of tuned these variables, we've reshaped them to make them fit better with the assumptions of linear regression. And therefore the linear regression process, the linear regression algorithm, will run more optimally. And because we have made these variables more normal, what's likely to happen, we'd have to do the entire analysis to see what's likely to happen is that because these variables are more normal, it's going to reduce our prediction error and therefore make the overall model much stronger and make better predictions for us, so long as we're keeping track of the transformations we are actually doing. So let's hop back into PowerPoint and finish out this video. Okay, that wraps up this video on the log transformation. Again, a very common transformation you will see in scientific papers, you will see it in economic data, you will see it in government data, you will see it all over the place. And usually if you see the log transformation, that means the original data had a high right skew to it, and therefore the transformation was done to make it more normal, which allowed, in our case here, for linear regression to perform much more optimally. And that's the word I want to use here, optimally. Could you use the original data in regression? Absolutely. But if you reshape the data to make it fit the assumptions of the technique you're using, in this case regression, then it performs much more optimally. And you can really squeeze out the performance of whatever algorithm or whatever technique you are using. Thank you so much for spending your valuable time with me. I hope you learned something that was very helpful to you, and I wish you the best in your career and everything going forward. I'll see you in the next video. Take care and bye-bye.